Hello and welcome. My name is Anthony Hill, and this is my CSC 381 workshop number 2. Um, I'm a junior at the University of Michigan, and today we're going to look at a language to see if it's context free. If it's context free, then it can be used it can be used with it can be used by a PDA. There can be a PDA created such that it would accept the language. And we're going to see if it isn't context free, then how would we create something that would accept strings of the given language? And we'll see how we do that. So the language is L1 equals X, such that X contains equal number of zeros, ones, and twos. Is the language context free? And equal number of zeros, ones, and twos. So a string would be like 0, 1, 2, for example, or 0, 0, 1, 1, 2, 2. Just for clarification. And we're going to see if it's context free. Instead of using PDAs to make one that would accept it, and then you have to create infinitely many, I guess. We're just going to try to prove one case wrong. And then if we can prove one case wrong, then the language is not context free. And to do so, we're going to use the pumping lemma. And what the pumping lemma does is it kind of separates the different pieces of the string to see if when it pumps, if the language would still accept it, or if the machine would still accept the language, rather. So the pumping lemma, if A is context free, then there is a pumping length P such that if T is a member of A and N is greater than or equal to P, then T may be divided into U, V, X, Y, Z. Where for each iteration, I greater than or equal to 0, U, V to the I, X, Y to the I, Z is a member of A. So there's your two push pop PDA iterators there, V and Y. So we're going to say that we're going to map 1 to 1, zeros, ones, and twos. And we're going to map 1 to 1 with VXs or VYs and Zs, because we're going to map, well, I'll show you here in a second. But VY has to be greater than 0, and VXY has to be less than or equal to P. Case 1. We have N 0 to the N, 1 to the N, 2 to the N greater than or equal to 0, such that N is greater than or equal to 0. And now we'll try to use the pumping lemma to on a simple string that would a simple acceptable string that this language would produce. And a super simple one for a string would be 0, 1, 2, and that's just because it's got an even number of zeros, even number of ones, or the same number of zeros, ones, and twos, rather, not an even number. That's not what we're trying to do. It's an equal number of zeros, ones, and twos. And we say that 0 will equal V, and 1 will equal Y, and 2 will equal Z. And that's our 1-to-1 mapping. If we try to pump with this setup, we see that it fails. So proof by contradiction. If we were to even pump the lemma 2 times, so the zeros get pumped twice, and the ones get pumped twice, the twos, there would only be 1, 2 still. So it would fail. And that's kind of what the limitations of push down automatas or your PDAs is. They can push and pop on the memory stack, but they don't have a movable read write head. And you can't, you would need another stack of memory in order to do this on a PDA, but it just unfortunately doesn't have it. So what do we have to do? Well, Turing machines have a movable read write head. And so we would be able to solve this if we had that. And thankfully, Turing machines do. So the 7 tuples of the Turing machine that I created with equal zeros, ones, and twos. M equals Q, sigma, R, delta, Q, zero, Q sub zero, blank, space, and F. Where Q is the finite set of states, Q0 to Q16. Sigma is the finite set of inputs, 0, 1, 2. R is the finite set. Sorry, finite set, not the finite set of states, finite set of inputs, finite set of tape symbols, 0, 1, 2, X, blank space. Delta function or the transition function, which is what's going to move our read write head. Q0 is the initial state, and we have the blank symbol. And F is the set of final states, and my machine only has one final state. So in order to solve this problem, we need a Turing machine. So let's pull that up. And I made one in JFlap, and this is it. Looks like a little leaf. Had to make it symmetric. I'm just moving this. Kept moving it back and forth. But anyways, how I created it. So I started with an initial state, okay, Q0. And I said, well, it's going to have to either accept a 0, a 1, or a 2. So that's 3 different paths that it's going to have to take. So I started, when I built it, I started on the 0 path. I built it thinking of zeros, ones, and two, like 0, 1, 2, just trying to accept that string. And so if I want to accept 0, 1, 2, I would build this right here. It's kind of like a loop, because it can accept multiple 0, 0, 1, 2, 0, 1, 2, or 0, 2, 1, and this loop right here. So it'll see a 0, it'll put down an X, it'll move the head to the right, and then it'll walk on zeros and X's to the right until it hits a 1 or a 2, which is what we need. We've already got a 0. Now we need either a 1 or a 2. So these are the only 2 possible acceptable outcomes. 1, see a 1, put down an X, move to the right, move the head to the right. Now we walk past zeros, ones, and X's. And here we need to get a 2 because we've already got our 0, we've already got our 1. So we have to have a 2 in order for it to accept equal number of zeros, ones, and twos. And the thing that's different on this is we're going to see that 2, we're going to put down an X, but we're going to move to the left because we've met all 3 of our, we have a 0, a 1, a 2, even number. We want to walk back to the beginning of the tape so we can get back to our initial state. So, okay, walk back left past the twos, the X's, the ones, and the zeros until we hit a blank space, which is at the beginning of the tape. And then we're going to move to the right and start the process over. And so after I had built this, I was like, okay, now all we need to do is to be able to accept, if a 1 came first or if a 2 came first, and then vice versa. So it's kind of just symmetrical loops. A test string, we'll try to test the 0, 1, 2. I'll show you this one real quick. 0, 1, 2. This is our simple string that failed the pumping lemma test. So we see a 0 in initial state. We see a 0 right here. We're going to put an X down, move to the right. See a 1, put an X down, move to the right. See a 2, put an X down, move to the left, and then walk it all the way back to the beginning. And we're back at the beginning, back to the blank space. And we move our head to the right, start all over. X's, we just went through that. We're gonna loop these right here because we have one set of zeros, ones, and twos. So we're gonna go next, next, next. Oh, it's seeing a blank space. It's all done. That sends it to the accept state. And we're green. That's good. It's all good. So we're gonna do a more complex, a little bit more of a complex one. We'll go 1, 2, 0, 0, 2, 1, 2, 1, 0, and 0, 1, 2. See what happens here. Should be an even number. So step this one times it sees a 1, so it puts an X down, moves to the right. We're gonna walk past ones and X's until we see a 2. Bam, takes that loop, that path, and then back to the beginning. And down that way it went. And that way. And we're full of X's on the tape. So it's gonna go to the accept state. Now let's do one that has an equal number of ones and twos, but we're gonna do them like this. One. I don't even know how many that was. Okay, so 4, 1, 2, 3, 4, 1, 2, 3, 4. This should accept. So we're gonna go 1. This time it's gonna have to transverse these ones. So it's gonna show you what happens when it hits a 1, takes a 1. Now it's gonna walk past all the other ones till a 2. Bam. And then a 0. Bam. And now it's gonna walk back left past all the X's, 1s, 2s, and 0s. And do this 4 times. Boom. All X's on the tape. And we accept. Now, one that fails, we'll say one without an even number of zeros, ones, and twos. We'll go 1, 1, 1, 1, 1, 1, 2, 0, 0, or 0, 1, 0, 1, 2, 0, 1. No, that's way off because there's way more ones here. So we're going to test this. It's got that set. It will go through and start finding all the sets of zeros, ones, and twos, but there's no 2 left on the tape. So it's not going to get to do this part right here, which then it's going to go to a reject state and rejects. So that's my Turing machine. Thank you for watching, and I hope that you learned something from this. Have a good day.